share the slides. Then current slide. I hope you can see the slides now.
Yes, sir.
Okay.
Yes, sir.
So let's start. So in the last class, we actually find out the reflection coefficient for T and TM case for oblique incidence, and if we have that medium, an isotropic medium, which we are actually going to design for uniaxial PML. So for that an isotropic medium, if A, B, and C parameter are having A is equal to B is equal to 1 by C, then the reflection coefficient for the T and TM case for oblique incidence was 0. So if it is 0 for T and TM case, it will be 0 for any arbitrary polarization, because arbitrary polarization can be decomposed into T and TM case. So this along the z-axis. So okay, so the condition was A is equal to B is equal to 1 by C. So if I actually take A is equal to SZ, in that case SZ 1 by SZ will satisfy A is equal to B is equal to 1 by C. So in this case, the wave was attenuating for the Z direction, because our interface was at Z is equal to 0, wave was attenuating at Z is equal to 0 when I have an isotropic medium with SZ 1 by SZ. A is equal to SZ is equal to B is equal to 1 by C. So we'll attenuate wave along the Z direction. Let's say if I want to attenuate wave along the X and Y direction, I can also take this lambda matrix or lambda tensor in the form SY 1 by SY SY. So for the wave to be attenuated along the y-axis, I can take similar value. You can do the similar derivation. Sy is equal to 1 by Sy Sy. Lambda x 1 by Sx Sx Sx. So if I take lambda x, lambda y, and lambda z like this, I will be able to attenuate the wave along the x and y and z direction. So if I multiply all these parameter, lambda, define lambda as lambda x, lambda y, lambda z. When I multiply all these matrices, what I'm getting is Sy Sz divided by Sx, Sx Sz divided by Sy, then Sx Sy divided by Sz. So in that case, I will be able to attenuate wave in any arbitrary direction. So I want to attenuate the wave in x direction, y direction, z direction. I have taken lambda x, lambda y, and lambda z. When I multiply all three of these, I will be attenuating wave along x, y, and z direction. So this is a lambda parameter I should take so that I should be able to attenuate wave along x, y, and z. So let us go back to the equation, Maxwell curl equation. This is the first Maxwell curl equation. Curl of y is equal to j omega epsilon 0 lambda e. So now epsilon 0 was that of the free space. Now we are in the n-isotropic medium, so we need to multiply by this lambda matrix here. Curl of E is equal to minus j omega mu naught lambda h here. Again, mu naught was that of the free space, but now we are in an isotropic medium, so we need to multiply by this lambda we have taken. And lambda turns out to be lambda x, lambda y, lambda z, so that we want to attenuate wave along x, y, and z direction. So let us try to expand the curl on the left hand side. We have this curl of h is equal to j omega epsilon 0 lambda e. So curl is like this. You can expand it, curl. So curl will have three components here. Right hand side also you have three components of the electric field Ex, Ey, Ez. This is a lambda matrix. This is j omega epsilon 0 or epsilon, doesn't matter. Left hand side you can also expand it, x, y component, z component. So this is the equation we have. This is the simple curl, and this is you have right hand side with the matrix lambda here. Let us just define a new variable which is called auxiliary. Auxiliary is basically helping or something like that. Meaning of auxiliary means helping. You have heard of auxiliary graph means helping bars. Just like that, we define an auxiliary field vectors here so that our analysis becomes easier. These auxiliary field vectors will make our analysis simpler. Look at this right hand side here. No? in the right hand side here, I will define a new variable dx, dy, dz. If I define a new variable dx as epsilon sz by sx ex, and dy as epsilon sx by x sy ey, dz is equal to epsilon sy by sz ez. In that case, I can rewrite the previous equation. I've taken out those commands here and define dx, dy, dz here like this. Then I can rewrite the previous equation as j omega sy sz sx dx, dy, dz. Dx, dy, dz are defined like this. These are called auxiliary field vectors. And this kind of Fdtd is called auxiliary field vector-based Fdtd. And what is Sx? Scale parameter x, a scale parameter y, a scale parameter z. It is kx plus sigma x by j omega epsilon. So previously we multiply j in the numerator and denominator. In that case, it becomes kx minus j sigma x by omega epsilon. That was the equation. It's the same equation. I've just put it in a different form. So if I multiply by j and j here, and what I'm getting is minus j sigma x by omega epsilon. That was the equation we have here. Same equation we have here. Scale factor is kx plus sigma x by j omega epsilon. Sy is ky plus sigma y by j omega epsilon, and sz is kz plus sigma z by omega epsilon. Sigma by epsilon is actually also called as loss factor and delta of the material. Loss tangent of the material. Loss tangent of the material. Anyway, so we'll define Sx, Sy, and Sz like this in this form. So in that case, I will just replace Sy, Sz, and Sx by the parameter we have chosen in this previous slide. So we just simplify. We have a j omega here, and this is a term you have here. Dx, dy, dz, and this is from the curl of the magnetic field vector. So let us look at the right hand side. Right hand side is having ky also plus sigma y by j omega epsilon also kz plus sigma z by j omega epsilon also kx plus sigma x by j omega. So I will separate these two terms. Then I write it as j omega kx kz kx ky kz kx dx dy dz and sigma y by omega sigma y by epsilon sigma z by epsilon sigma x by epsilon dx dy. I will just separated these two terms. So there's a plus sign here. So I will separate this term and this term. So plus, this is what we have in the right hand side. And one more thing is that what is j omega? J omega is del by del t. So we will replace that. And Fdtd program should have a time varying variable also. So j omega will take care of that. J omega is del by del t. So del by del t of this first time, second term doesn't have any derivative. So I can take in again this del by del t. This is ky, kz, and kx are independent of time. So only dx, dy, dz, these are the auxiliary fields. They will be dependent on time. I do partial derivative with respect to dx, dy, dz, del by del t, del by del t, del by del t, and this term here. So there are three components here: 1, 2, 3, 1, 2, 3 here, 1, 2, 3 here. Just equate it. What you have is in component wise. This is the equation you have: del z by del y minus del y del z. This from the first term in the right hand side. This from the second term in the right hand side. Similarly here also there will be three components. You just equate the three component x, y, z component. You have three equations now. You can also do it for the second Maxwell curl equations. Curl of E is equal to minus j omega mu del what is the lambda h. So here also you can do the same thing like last time. So curl of E you can express in this form. The right hand side you have minus del by del t of this first term. This is the second term you have here, similar to the last case. So you'll have again another three components of the Maxwell curl equation, second Maxwell curl equation. These are the three components: 1, 2, 3, and from the previous Maxwell curl equation, you have another three. So you have 6 equations. Okay. How do you do the Fdtd update equation? So here we have another variable which is called auxiliary field. So auxiliary field is dx, dy, and dz, which was defined as epsilon sz by ss, ex, and so on. So let us try to write the Fdtd update equation. See, basically 3D Fdtd have 6 equations, but here we also have 3 auxiliary fields, dx, dy, and dz. So we'll have extra 3 more equations. for the update equation. So that update equation we want to come up for dx, dy, and dz. 3 equations from the Maxwell curl equation. So you'll have 6 equations for the Fdtd 3D update equation. But here you also have auxiliary field update equation. We'll have 3 more. So we'll have total 9 update equations. So how do I come up with the update equation for dx, dy, and dz, which are called auxiliary fields? Can be from this relation you have here. So you just transfer this sx to the left hand side. Then what you have, sx dx is equal to epsilon sz ex. What was sx? Sx was kx plus sigma x by j omega epsilon. What was sz? Sz was kz plus sigma z by j omega epsilon. So now you can simplify it. For example, whenever you just take this j omega epsilon, multiply it here, you also take j omega epsilon, multiply here. J omega means del by del t. So del by del t of kx dx plus sigma x by epsilon dx. Here also del by del t, because you have j omega term here, del by del t of kz ex plus sigma z by epsilon ex. Outside the bracket you have epsilon. You can further simplify it. Final equation would be something like this. So this is one update equation you can write from here. Similarly, you can also write update equation for dy from this expression, derive it similarly, dz also. So in total, you'll have 3 equations for auxiliary field update equations. This is the first one, second one, and third one. So let us try to discretize this. Okay. You have 6 of them, I think. dx, dy, dz, just like the dx, dy, dz also you have. Let's go back. We also have dx, by, bz, no? dx, by, bz with respect to hx, hy, hz. So you'll have 3 equations here, 3 equations there. So you'll have total 12 of that equation for Fdtd. 6 for the auxiliary field and 6 for the 3D Fdtd. Okay, let us see how to discretize this auxiliary fields. Dx is auxiliary field, electric field. So dx actually follow the discretization of the electric field because dx is dependent on ex. Dx is dependent on the electric field. So dx would be discretized like this. It will be discretized over the integer time step. So if I want to do partial derivative of dx with respect to time, then dx at n plus 1 minus dx at n divided by delta t. What is the location in the space? Dx will follow that of the ex. Ex was at the half of the edges along the x-axis, so I plus half jk, I plus half jk. So dx and es has the similar kind of discretization. And integer time steps, half integer, half space time step for the x component. And one more thing is that on the right hand side you have something like dx. See, let's look at the, go back. What do you have here? Let's say dx here, dx here. So this is del by del t of dx, but this is dx here. So dx, we don't know the value of dx at n plus half. So we don't know the value of dx at n plus half. So we actually take the average of dx at n plus 1 and dx at n. And location is that of the electric field, which is I plus half j comma k, I plus half j comma k. So that's how you actually discretize dx. Dx is dx at n plus 1 plus dx at n divided by 2, and the location over the space will be I plus half comma j, I plus half comma j. So dx is almost like electric field, Ex. So you can substitute it. Magnetic field will actually follow that of the 3D Fdtd cube. You can substitute in that equation, then you can discretize it like this. Let us go back to the equation. We are actually trying to discretize this one. Okay, what is this equation? This equation is about respect to Iz. Iz, for example, if you want to find Iz is calculated at the half integer time steps. So n plus half here. This is at the center of the faces in the xy plane. So I plus half, j plus half. Partial derivative with respect to y. So I plus half, j minus half. K would be integer. And you are doing partial derivative with respect to z. And xy is at the center of the faces along the xz plane. So I plus half, k plus half, I plus half, k minus half. at the half integer times step n plus half here. And the partial derivative we have just discussed now, dx at I plus half j comma k, n plus 1 minus n divided by delta t. Dx at n plus half, you can find out dx at n plus 1 dx at n divided by 2. If you want to discretize electric fields are calculated at half integer times step, magnetic field at half integer. You just follow that of the 3D Fdtd. So this auxiliary field update equation discretization is very similar to your 3D Fdtd discretization. Dx will follow Ex, dy will follow Ey, and the dz will follow the Ez. So you can combine the terms which are dependent on n plus 1 and n in the right hand side. You have two of them, n plus 1 and n. So you combine those terms. Then you can define new constant. You can define new constant after you combine those terms. Let's say I want to find dx at n plus 1. I can find dx at n plus 1 from dx at n. And this is a magnetic field dependent parameter. We have already combined dx at n plus 1 and dx at n. And this constant, you transfer it to the left hand side, divide it. That's what we are doing here. So you want to find dx at n plus 1, you calculate dx at n, and this constant you transfer it to the right hand side and divide it. So finally dx at n plus 1 I plus half jk is equal to some constant c1 at dx at n, then c2 dx. So what is c1 dx? C1 dx is the metal dependent parameter. You can find out 2 epsilon ky minus delta t sigma y divided by 2 epsilon ky plus delta t sigma y that we have derived just now. Sigma 2 dx, c2 dx is basically 2 epsilon delta t by 2 epsilon ky plus delta t sigma y. Just try to find dx at n plus 1. You don't want any constant here. You transfer all the constant to the right hand side. The final constant you denote it by c1 dx and c2 dx. We have two constants here, c1 dx and c2 dx. And you also find out the magnetic field Iz at different locations, and Sy at different locations. You should be able to find dx. So this is the update equation for dx. So if you want to do the calculation for Ex, then look at this here. Right side you have del by del t Ex, and you know how to do it. So Ex is calculated in integer times step, so n plus 1 and n divided by delta t. What is the location of Ex? Ex is I plus half j comma j, I plus half comma j. So Ex is equal to Ex at n plus half, I plus half comma jk is equal to, let's say you also have Ex here, no? Ex here. You are actually going to calculate at n plus half, but we do not know the value of Ex at n plus half. I actually take the average of Ex at n plus 1 and n divided by 2. Location is same, I plus half j comma j, I plus half comma j. Then again, you rearrange the term. Then let's say if I want to find Ex at n plus half time instant, then I need to know dx at n plus 1 and dx at n and Ex at n. From the equation, you derive it, then transfer all the constant to the right hand side. Then you can define a new constant C1 and C2 and C3. C1 is defined like this, C2 is defined like this, C3 is defined. That's a simple derivation. So final update equation would be of the form Ex at n plus 1. Location is I plus half j comma j. Should be related to dx at n plus 1, I plus half j comma j. See the location, time location, space location you need to worry about. So time location is always integer for Ex, dx, and Ex, dx. So all the time locations are integer time steps. And what is the space location? The space location is I plus half j comma j. Ex and dx has the same space location. So if you want to find Ex, then you multiply by constant C1 Ex with dx, then C2 Ex with dx at n, and C3 Ex with Ex at n. These are the constant we have derived. So these parameters are material dependent parameters. They are going to change at different locations. That's the only thing you need to worry. So at different locations, if you have different medium, same medium, then you have to calculate it only once. But if you have different medium, because wave is propagating in any place, it can hit walls, it can go anywhere, and it can go into the water. So different location, you'll have different value of this material parameter. So if you are doing simulation for free space, you don't need to worry about it. It's always fixed everywhere. So all this constant It's not going to change. But if you are in different medium, one medium to another medium, then you have to keep on updating this value of the C1EX, C2EX, and C3EX. Okay, so that was about the auxiliary field update equation. We will have 6 extra auxiliary field update equation along with the electric field and magnetic field. So for every component of the electric field, you'll also have auxiliary fields. For every component of magnetic field also, you'll have auxiliary fields. So you have to write extra 6 more update equation for the FTD program. So in total, you'll have 12 update equation for the FTD program. Okay, so there are some issues with the PML. So that was about the PML. No? When you want to implement PML, you can actually use the auxiliary field update equation for a PML. Inside the PML layer, you have to do auxiliary field update equation also. That we have already discussed. We have discussed for, I think, 2 cases. You can actually do similarly for the remaining 4 cases. So now there is some problem with this PML. So PML actually is one area of research for the FDTD community. So 3D update equation, 1D update equation, 2D update equation is already fixed. It's already derived and you don't have anything more to do in that. But when you are doing research in the area of FDTD, PML is one area where people are doing research nowadays every day. There will be some improvement in the PML there. We have discussed about some of the PML layer. The one we have just discussed is the uniaxial PML layer. It's also quite good. But there are some issue with this uniaxial PML. We started with the Behringer's PML. Behringer's PML was not good enough. Then we went for the uniaxial PML layer. And that actually kind of PML use anisotropic medium to absorb the waves. But even then also uniaxial PML also have some issues. That's what we're going to discuss now. So there is some kind of reflection at the boundary for PML. So you have seen that if you want to reduce the effect of boundary at the PML layer, you actually use scaling parameters. Basically, you have considered the PML layer and free space. When you go from free space to PML layer, there's a sudden change in the conductivity. So if you want to minimize reflection at the interface between the free space and PML layer, you actually scale the conductivity in form of a polynomial, no? Second order or third order polynomial. Even then also there is some issue, especially at the low frequencies. I think there are some students who are working in the low frequency. So if you go for low frequency, even if you do that scaling, no, you actually assume the gradual increase in the conductivity inside the PML layer, then also it will not solve the problem of reflection, especially at the low frequency. You can see that, for example, if you are scale factor is of the form Sx is equal to Kx plus sigma x by j omega epsilon. So now this scale factor, what happens when omega tends to infinity? Omega tends to 0. When omega tends to 0, this will become infinite. This will become infinite. So this is a problem. No? When you are going for lower frequency, even if your PML layer was working properly, but when you go to lower frequency, there will be a lot of errors at the low frequency because of this issue. When omega tends to 0, this term becomes infinite. So is there any way to overcome that? That is another PML we are going to discuss. The effect of the low frequency can be clearly observed by adding one extra term here, alpha x. Sx was Kx plus sigma x by j omega epsilon. So now we just add one extra term here, alpha x, which is a positive number. What happens? We want to see what is the effect of this scale factor at the low frequency. We can see that. So now let's assume that propagation constant gamma x is jkx. So now what I meant to say is that there is a wave propagating along the x-axis. So when I multiply by this scale parameter with this propagation constant, what happens? Let's try to see that. So if I multiply by this scale parameter to this propagation wave vector, actually what you have is exponential minus j, exponential minus gamma x is the wave propagating along the z-axis. And here in this case, I assume that gamma x is jkx. So in that case, exponential minus jkx, x is what? It's a wave propagating along the positive x-axis. And I multiply by a scale factor here. That's what I have in the PML layer. I will multiply by a scale factor with the propagation constant. So I multiply by this scale factor. What is our scale factor? Kx plus sigma x by alpha x plus j omega epsilon. I have actually added alpha x term in the denominator so that I want to observe the behavior of the wave with respect to frequency. So now, what happens to this wave when you have high frequency? High frequency, then what happens? High frequency alpha x plus j omega epsilon e. High frequency means omega is 2 pi f. So f will go higher and higher. So omega will also become larger and larger. So this term would be the dominant term here. Alpha x would be neglected. So omega would be much lesser than alpha x by epsilon 0. So I can neglect alpha x here. What I have is uniaxial PML you have here. So when I neglect alpha x, then this is that of the uniaxial PML. That is the PML we have just considered. Alpha x are additionally added here intentionally. So when omega is high, frequency high, alpha x effect is not observed here. So now let's look at the other way around. When you have a low frequency means this omega term would be tending to 0. Alpha x is a larger term now. So in that case, alpha x by epsilon 0 would be much greater than omega. In that case, what you observe is this term, omega term is becoming 0. In that case, what you have is exponential minus jkxx minus exponential minus jkx sigma x by alpha xx. So this is a wave which is propagating along the z-axis, x-axis. You don't have any attenuation. Attenuation will be there when we have something like exponential minus alpha x. Alpha is a positive number. But here what we have is exponential minus kxx. So this is a wave propagating along the x-axis. There is no attenuation at all at low frequency. So that is the problem. That's a problem. So we define something called breakpoint frequency between the high frequency and low frequency, where there is a breakpoint. Till high frequency is there, your PML layer will behave like uniaxial PML, but when you go to low frequency, your PML layer is not going to attenuate wave at all. So if you actually enclose the whole solution space with another metallic boundary condition, at low frequency, wave will propagate to the PML layer without any attenuation. It will hit the boundary, then it will come back. So there will be a lot of reflection, there will be a lot of error at the frequency. So the uniaxial PML we have designed cannot work for low frequency, and many of the people like high power, low frequency applications, no, high power engineering or whatever, that high power electromagnetics people, they work at low frequency. But this uniaxial PML, it doesn't work at low frequency. As you have already observed, that wave was propagating without any attenuation at low frequency, so all of them will be reflected back. So is there any way to overcome that? That's a discussion we'll be doing. So I think we don't have time for this now. I'll stop here.